So good afternoon to everyone. I'm Pablo. I'm a PhD student from the University of Sevilla, and today I'm going to present this work that is titled Influence of Volumetric Locking on the Combination of Plasticity and Phase Field Models for Fracture. The outline is this one as follows. First, we are going to introduce the problem by setting the objectives and the motivation behind these works. After, we're going to set the computational model that works on modeling the ductile fracture. And also, we are going to introduce different kind of methodologies to treat this kind of volumetric locking. With these implemented methodologies, we are going to set some examples to validate and to see the volumetric locking. And last but not the least, we are going to set some conclusions and the future work that we will develop. As for the basis, what we want to do is to set a ductile fracture model that works on the interrelation between two fields, the plasticity and fractures. On the side of fracture, we are going to work with the phase film approach to fracture that will be in charge of the nucleation, crack opening, and the crack development on our model. And on the other side, the plasticity is going to be modeled by some kinds of basic models that are the von Mises model, Morkulov, and Drucker-Praga model. As for the specific objectives, what we are going to see is that working with this kind of models can arise some objective problems. One of them is what this is known as volumetric locking. Volumetric locking, briefly, is the inability of the mesh to correctly catch the different, how can I say, the different volume that are on the elements. For treating this kind of problem, in the literature, we can find some remedies for that. We're going to focus on the first two that are the V-bar method that works on modifying the methodology of the finite element, and more precisely on the V operator. On the other side, with gradient plasticity, what we are going to do is to set a non-local plasticity model. As for phase field, we are working also with a non-local model. We are going to get two length scale parameters, one for the plasticity and one for the phase field. As for the system of equations, we can group them in three groups. For the equilibrium, the local plasticity, if we are not taking now into account the non-local plasticity model, and phase field. For the phase field model, we can change the Karush-Tucker conditions with a simple and unique evolution equation that is ruled by a new variable that is this one, H, that is the historic variable that depends on the elastic energy, the plastic dissipative energy, and we can also add an energetic barrier as known as a threshold. With that, we can, using the principle of virtual works, we can get the system that can be implemented in our finite element program, and we get the residuals and the stiffness matrices for the displacement field and for the phase field. For the first methodology, that was the V-bar method, we're going to do is work on the residual and the stiffness matrix for the displacement part. The V-bar method, what does mainly is to work independently on the isochoric part and on the volumetric part of the strain field. How we do that? With these three bullet points. In the first part, what we do is introduce a new variable that is known as omega. Omega, what it does is setting an average value of the volumetric part of the strains in the Gauss points. With that, what we are doing is modifying the V operator for the volumetric part. The second task is to set the new definition for the strain field with the parameter omega that we defined before. And last but not least, what we do is also setting a full integration path for the deviatory part and a reduced integration path for the volumetric part. That is the main goals for the V-bar method. As for the non-local plastic formulation, we work on the basis of Mige, Professor Adakil, and Forrest, and we are using is the micromorphic, as we know, as the micromorphic approach to Garnier state models. What is mainly that we, in 1D, one dimension, we can have this kind of problem where we can see some irregularities in the boundary. In this case, the boundary is the zone that differentiates the elastic part with the plastic zone. This is what we know as or could be the locking phenomena. If we use this kind of models, the non-local plastic formulation, what we do is soften these parts in order to regularize it. How we do that? With the modification of the plastic energy part by setting a new term dependent on the length scale and a penalty parameter. With that, we can set the dissipative force field and the balance equation, and with the balance equation, we can get the equation that we have to implement in our model in order to get this variable. That is the non-local part of the plastic field that we have to calculate. As for the examples that we want to analyze in this brief presentation, we are setting the example of the open hole, where we are going to see the different pathologies that we can have with the volumetric locking, and also rigid footing in order to introduce the non-local plastic formulation. As for the open hole system, we are working with this kind of a specimen in plane strain conditions are subjected to tensile loading. We will work with two meshes, one that is orientated 90 degrees to the horizontal axis and one is orientated 45 degrees to the horizontal axis. And we also will differentiate two cases that are the B matrix formulation, that is the normal B operator, and setting the B bar matrix formulation, that is the one that I explained before. As for the results, for the mechanical response, we cannot see such a difference. This is negligible. For the bearing capacity, all the models predict the same bearing capacity, but if we see or we pay attention to the morphology of the shear band, we can see that all of them agrees on setting the shear band orientated 45 degrees to the horizontal axis. That in the theory is technically correct. But for the width of the band, we can see some differences. With the methods that works with the V-bar, we can see that the equivalent plastic strain is more localized, and the width of the shear band is more narrow. And as for the problem of the bearing capacity, we are going to study the one that is called the Brannan-Hill solution that works on setting a long straight foot resting on a material. In this case, we can work on a soil. With that, if we calculate the collapse system, we get this kind of solution, and we are testing it with this scheme. As for the applied cases, we're going to see how the solution works with local plastic formulation plus phase field, and with non-local plastic formulation plus phase field. As for the local plastic formulation, we now can, in the mechanical response, we can now see differences on setting the bearing capacity. The blue one is with the normal V method, and the orange one is with the V-bar. We can see that the one that predicts correctly the bearing capacity is the V-bar, whereas the normal V method overestimates the bearing capacity due to this volumetric locking phenomena. As for the morphology of the yield surfaces, we can also see differences. In the normal V operator model, we can see the formation of a vertical shear band, whereas in the V-bar method, we can see that it correctly predicts the yield surface that the Brannan-Hill method says. And as for the non-local plasticity model, we have three solutions. We have the displacement field, the non-local plastic variable field, and the phase field. As for the displacement field, we can see that it correctly reproduces the yield surface. We can see the different bodies that are formed during the collapse system. And as for the non-local plastic variable field and the phase field, we can see that it goes really well to the qualitative solution of the Brannan-Hill theory. And also we can control with this, because in this case, as I said before, we count on two length scales. We can also set the width of the damage process zone according to the width of the plastic zone. And as for the conclusions, we were able to see the problem that can arise on locking phenomena working on linear elements. We implemented some methodologies, the V-bar method and the non-local plasticity model, in order to alleviate this kind of locking. And also it helps to develop a more robust ductile fracture model in order to study this kind of cases. And as for future work, we wanna, in this case, we work with normalized ductile fracture methodology, but we can also work with others like Mige or Bourdain. Also, we can extend the application of the non-local plasticity model to other GL criteria. And last but not the least, the application of this method and of this methodology to more complex cases. And if you have any question, I will be glad to answer it. Thank you.